steady state of the universe. As the name suggests, it proposes that the universe does not have a beginning, nor it will ever have an end. During 1960s, the most famous theory of the universe's beginning was called the steady state of the universe, which was proposed by Dr. Jayant Narlikar and Dr. Fred Hoyle. The theory was a Machian and conformal theory of gravity that originally fits into the quasi-steady state model of the universe. It was inspired by the Wheeler-Feynman observer theory of electrodynamics, where the gravitational constant g is arbitrary and is determined by the mean density of matter in the universe. Everything was going well, but then a 23-year-old PhD student, Stephen Hawking, read the paper. He immediately thought that the theory is incompatible if our universe is, in fact, expanding with acceleration. However, at that time, the accelerating expansion of the universe was not known, which resolves the divergence issue because of the cosmic event horizon.
Your calculation is wrong. The advanced field diverges.
So, he showed that the theory of steady state of the universe reduces Einstein's general relativity in the limit of a smooth field model of particle distribution constant in time and space, and that was certainly not possible. But is it? If yes, then why, indeed, is there something rather than nothing? How did everything begin? What was there before the beginning? Where did all the materials come from that created the Big Bang? What happened in the first instance to the creation of that material? And lastly, why are we here? These profound questions have danced in the tapestry of human curiosity, transcending generations and cultures. To delve into the cosmos, we extend our sensory reach through instruments like the Hubble and James Webb Space Telescope. These remarkable feats of engineering have unveiled fragments of the universe's secrets, illuminating but a fraction of its grand tapestry. Day by day, we scrutinize the heavens, capturing enchanting vistas of distant galaxies, nebulae, and celestial phenomena, each snapshot expanding the boundaries of our cosmic understanding. Through these optical windows, we have glimpsed the birth and demise of stars, pondered the intricate choreography of galaxies and their cosmic collisions, and unraveled the enigmas of black holes. By measuring the redshift of remote galaxies, we peer back eons into the past, glimpsing the universe's infancy. But with all these magnificent discoveries, we'll still have numerous unanswered questions. Why, when, how, and where? Can we ever answer these questions? Well, you have to keep watching. The last star will slowly cool and fade away. With its passing, the universe will become once more a void without light, life, or meaning. Yet, other theories beacon from the shadows. Might our universe's Big Bang have evolved from a prior void, mirroring the desolate future awaiting us? Here, the first theory unfolds. Theory 2 invites us to abandon the notion of a singular origin, proposing an eternal universe in a perpetual expansion and contraction. A cosmic world where reality remains untouched by the time scares. Theory 3 takes us further still, conjuring infinite universes, each endowed with distinct laws, constants, and states. Our universe merely a solitary entity within an infinite tapestry where every conceivable outcome materializes. Finally, Theory 4 shatters conventional perceptions, suggesting our reality is but a complex simulation designed by an advanced intelligence. Our world, from physics to consciousness, mere manifestations of an intricate computer program. The relentless advances of technology and our capacity to craft lifelike virtual realms advocate for the plausibility of this proposition. The universe perplexes us, Particles blink in and out of existence. Dark matter, an invisible and mysterious entity, dominates our cosmic expanse, defying observations. And dark energy, an enigmatic force, widens the cosmic fabric, countering gravity's embrace. Then the Big Bang itself, the narrative of our cosmos's genesis, unfurls. Yet, even the narrative offers illumination for what happened post-Big Bang, but the veil shrouding the events before remains. How did all matter, energy, space, and time emerge from a point of infinite density and temperature? The cosmos teems with puzzles. Some theories venture that a prior void, akin to our universe's anticipated end, triggered our Big Bang. The journey into the origin of matter, atom, and molecules highlights that they too did not initially exist. The early universe harbored fiercely energetic particles, stifling the formation of complex matter. It was only through a gradual expansion and cooling that atoms like hydrogen and helium found a nurturing cradle. Like someone once famously said, "See, look at yourself and look at all the things around you." This is what hydrogen atoms do when given 13.8 billion years. Digging further back in time, we encounter the emergence of protons and neutrons, the building blocks of atomic nuclei, around 1,000th of a second after Big Bang. But this does not address the conundrum of something from nothing. Venturing into speculative physics, we enter the grand unified epoch, where matter and antimatter coexist in precarious balance. Each matter particle had its own antimatter twin, annihilating each other in brilliant flashes of energy upon meeting. Yet, where did all these particles themselves spring from? Quantum field theory posits that a seemingly empty vacuum teems with energetic fluctuations, occasionally gives birth to particles that swiftly vanish. The notion of matter manifesting from empty space challenges the concept of creation ex nihilo. But inquiring minds push further, querying the origin of space-time itself. Thus, we journey into the fathomable Planck epoch, an era of such primordial youth that our established physics flatters. Space and time surrenders to quantum whims. Here, physics unifies quantum mechanics, governing the minuscule with general relativity, which presides over cosmic scales. A unified theory of quantum gravity, however, eludes us. String theory and quantum loop gravity makes attempts introducing a paradigm shift. In this view, space and time become emergent concepts, arising from quantum bedrock that lies beyond our intuitive grasp. In the Planck epoch, our ordinary comprehension of space, time, and causality flatters. Nonetheless, all potential quantum gravity theories depict a physical backdrop within the Planck epoch. But the riddle remains: what gave birth to all this? In the absence of a comprehensive theory that interweaves all these threads, a definitive answer eludes us. Thus far, physics has unearthed no instance of something emerging from absolute nothing. The endeavor to fathom how something can arise from nothing compels us to grapple with the quantum state of the entire universe during the Planck epoch, an era of profound speculation. So, the answer to the question if the universe is a steady-state universe or it did had a Big Bang, well, I don't have it. And I guess no one else have right now.